And from Lewis Carroll, also known as Charles Dodgson, but most people don't know him as Charles Dodgson. He was a mathematician. He did logic. But he also wrote the book Alice in Wonderland. And so what did he say? It's no use going back to yesterday because I was a different person then. And I like this idea. We are always changing. And one of the things that you might think at this point in life is like, I can't change. I can't learn. I've become who I'm going to be. And that's not true. You will look back and you say, well, think about who you were 5 years ago. You were very different back then. And as much as you've changed in the last 5 years, you're going to have as much or bigger a change in the next 5 years. And that's always going to be true. You're always going to be changing. You're always going to be improving in some areas and maybe recessing in others. But life is a journey, and so keep moving forward. Now, what's our goals for today? We're going to talk about a couple of ideas, and we may not get to all of them, but that's okay. We still have the next lecture. We're going to talk about conditional probability. So there's a condition. So it's still a probability, but we're going to say, look, I want to understand the probability that a certain event happens. So let's say A is what we're interested in. I want to know what's happening with A. But now I'm going to add a condition, and that is that there's another event which I already know did happen. So we're going to talk about the probability of A given B. So this should be read as, what is the probability that A happens given that we know B happens? And it turns out that it's not so hard to compute. It's the probability of the intersection, A intersect B, divided by probability of B. We're going to talk about probability trees. This is a way to sort of represent what's happening visually to give us information and help us answer questions that will arise. So they're very useful in practice, at least for the kind of problems that we're going to be doing. We'll talk about the ideas of things being independent. Now, what does it mean if things are independent? Well, it says, look, they're not related. They're completely separate from each other. So if I want to say, what's the probability of A given B? Well, if A is independent from B, it says, like, look, knowing that B happened gave me no information. So that's the same as saying it's the probability of just A. And it turns out that one way to say this is equivalent to the following. The probability of both A and B happening, so that's the intersection, is equal to the probability of A times the probability of B. So that's independence. And then finally, we'll talk about Bayes' formula, which looks scary and intimidating, but is not as bad as it comes across. Essentially, we say, well, it's easy for us to talk about what's the probability of A given B, but we want to turn the tables. What's the probability of B given A? Can we figure that out? And it turns out we can. Now, I'm underselling the importance of Bayes' formula. When it comes to statistics, this is probably one of the most important ideas that exist. There have been whole books written about Bayes' formula and its influence in the world. And even whole subjects of mathematics called Bayesian statistics. And so it's a really useful tool. All right, let's begin. We'll start with the idea of the conditional probability. And sort of underlying this whole conversation today is we were trying to understand, how do events relate to each other? Okay, so we're talking about the probability of A given B, or the probability that A is true given that B is true. And visually, we can go back to our Venn diagrams. So we have this idea of saying, well, we have this space of events. Everything that could possibly happen, you are a universe of possibilities. And we have two things, A and B. Now, what happens? Well, what happens is we know that B is true. We have information given to us. So what happens is instead of having our whole universe, it collapses down to a much smaller thing. So we go from the big picture, and now that we know B is true, we shrink down to this small piece. So that's what happens when we know something is true. It reduces down our space. And so now we say, well, look, the only part of A that's left is this piece of the overlap. And so we say, okay, what happens? Well, now we can say the probability of A given B is I come in here, so it says, I want to know how much of this is taking. Now, what portion of the space is that? And so we say, well, to figure that out, I just figure out how big is this piece. That's the probability of A intersect B. Then I have to scale it. And I scale it by dividing by the probability of B. And that's the idea. Nothing too scary. All right. Well, let's do a problem. We have a fair 20-sided die. In the book, it uses 11-sided die, but I thought, let's be fancy. We'll go 20-sided. Fair 20-sided die is rolled. And we have two possible events. We have first the event A, that a prime number is rolled. And then we have the event B, an odd number is rolled. And we're asked the following. Find the probability of A given B. Now, before we get too far, let's remind ourselves, if you see a word like fair, what does that mean? We say something is fair. If we have a coin, if we toss it and we say it's fair, what does that mean? What's a fair coin? What's a fair die? It means equally likely. So everything is equally likely. Now, the nice thing is when you see the word fair, you say, if everything is equally likely, what it really means is the following. It says, this becomes a counting problem, which is good. And I think a lot of nice problems in probability can be done by counting things. Okay, so that's just a note. All right, so how do we do it? Well, we can think about our space, and there's a lot of ways we could do this. Let's think about our roles. So we have our two places. We have our A and our B, and I'm already regretting my choice to try to do this, but that's okay. In for a penny, in for a pound, right? As the saying goes. Well, now, oh my goodness. What do we have? Well, we have the numbers 1 through 20, right? 1, 2, 3, up to 20. And what we can do is we can actually just fill up our space, and then we'll be able to say things a little bit easier. And on a side note, I made a video for the college, the LAS college, a few days ago. This was right before break. And they gave me a script. And they said, the number 1, that's a great choice. 1, that's a prime number. Wait, is it? Does anybody know? Is 1 a prime number? Turns out we don't consider 1 a prime. All right, so if 1 is not a prime, where would it be? Is it in A? Is it in B? Is it in both? Is it in neither? That's the trickiest one. After that, it'll become much easier. It's in B, but not in A. So there's 1. 2, well, it's not odd. Is it prime? Yes. In fact, they say 2 is the oddest prime number because it's the only one that's even. Okay, so we can keep going. So then we have 3, 4 is neither, 5 is, Sorry, 3 doesn't belong there. 3 belongs here. It's in the intersection. It is both prime and odd. 3, 4, 5 is both prime and odd. 6 is neither. 7 is both prime and odd. 8 is neither. Where does 9 go? Well, 9 is not prime, but it is odd, so it goes over here. We have our 10, 11, both odd and prime, 12, 13, both odd and prime, 14, 15, where does 15 go? It also goes into B. But not A. It's odd, but not prime. All right, 16, 17, 18, and 19. Oh, it turns out there's a lot of small prime numbers. Well, that's a little bit misleading. Okay. So, what can we do? Well, we can do a couple of things. We can just say, look, let's reduce the problem down to this part right here. How many numbers are inside of B? In other words, how many odd numbers are there? From 1 to 20. Half of them. So there's 10 numbers in here. How many numbers are in the overlap? Well, 7. So what's the probability of A given B? If we just restrict our space, we can say, look, there's 7 things in our overlap by counting over 10 things in our total space. So 7 out of 10. 70% chance. Now, if we do it in terms of the formula, because we can do it in terms of the formula here, the probability of A given B, we can say, well, that's the probability of A intersect B over probability of B. Now, one thing the book mentions, and I think this is kind of a nice idea to point out, is that on the left-hand side, we're working in our smaller space of B. In the right-hand side, we're working in our bigger space of the whole thing. So, what's the probability of being in the intersection? Well, there were 7 things in the intersection, so the probability of being in the intersection is 7 over 20. So that's the numerator. What's the probability of being inside of B? Well, half the numbers are odd. So that would be a 10 over 20. And then the over 20s cancel, and you get 7/10. So you can look at things in 2 slightly different perspectives. All right. Let's try another one. So we get the hang of this. We have a circular spinner, and it's going to land in one of 6 spaces which have different sizes. So here, things are not fair. They're biased. And so how can we think of this? Well, we can think of it as you have a big circle, you have a little spinner, but now you have some pieces which are relatively thin, and then you have some pieces which are relatively large. And so because of that, it causes it, you're more likely to fall in the green, which is bigger, than to fall into the red, which is smaller. So what can we do? Well, we can assign the probability of falling into the slots. So there's 1 through 6. Those are our possible values we can get with our spinner. And we have probabilities of falling in each one. So the probability that you get a 1 is 0.1. Probability you get a 2 is 0.2. Probably get a 3 is 0.1, probability 4 is 0.1, 5 is 0.3, and 6 is 0.2. Now, as a reminder, there's a couple of things that should be true. There's always a sanity check that you can do on things like this. One thing is that the probability of any single event should be between 0 and 1. Okay, that's true. The other thing is that what should be true about the sum of all the probabilities? Do you remember that? If you sum up all of them, what should you get? 1! Yes! This reminds me of the classic advice of taking a math class. If you're taking a math class and the teacher asks a question, there tends to be 3 correct answers. 0, 1, or it's written somewhere on the board. And today the answer is 1. Why? Well, if you sum up the probabilities, you're saying that's probably that something happened. And something always happens. When you do this, something has to happen. Now the question, what is the probability of the number landing on something bigger than 4, given that it has landed on an even number? All right, so when you see a word such as a given that, that's a signal to you that this is a conditional probability type question. So we say, okay, we have a conditional probability, and now we'll say what? Well, if we work it out in words, we have the question, we want the probability that our number we land on is bigger than 4, given that we land on an even number. So that's, well, usually we shorthand this and say, oh, let A be this, let B be that. But that's what we're after. Okay, so what can we do? Well, we can say, well, that's the same as the probability of the number we land on is bigger than 4, intersect, we land on an even number, divide by, and now you kind of get the idea of like, oh, now I understand why they just like to say A is this and B is that. It's because they don't like writing things out in longhand. This is true. You don't become a mathematician to write long sentences. You like good notation. Okay, so let's talk about these probabilities. The upstairs, when you see intersection, that means that both things have to be true. So we need to have a number that we land on needs to be bigger than 4, and we have to land on an even number. All right, well, how many numbers are there which are bigger than 4 and even? There's one number, right? 6. So we say, okay, the probability that both things are true, we add up one thing, it's 0.2. Now, what's the probability that we land on an even number? Well, we say, what happens? Well, we have the 2, 4, and the 6. So how do we find that probability? We can add up. So it'd be 0.2 plus 0.1 plus 0.2. So this ends up being 0.2 over 0.5. Well, if you multiply both top and bottom by 10, that's the same as 2 over 5. 2/5. 40%. Okay. Any questions? Great. Okay. Well, moving right along. We can get a nice sort of, I can't remember what they call this in the book, I think multiplicative fact. But you can start with the conditional probability that says the probability of A given B is the probability of the intersection divided by probability of B, and say, well, let's solve for the probability of A intersect B. And that's not so hard to do. You just multiply across, and you say, well, that's the probability of B times the probability of A given B. So the probability of A intersect B is the probability of A given that B is true times the probability of B. And it makes sense. You say, well, I need to know if A intersect B, this is both A and B are true. So I need to know that B is true. And now that I know that B is true, I have to say, well, what's the probability of A given that B is true? But you could have, of course, started with the other thing, which is probability of B intersect A. Well, that's probably, again, the intersection. Sorry, probability of B given A. It's probability of the intersection divided by probability of A. And so you can get our other way to write it. All right, so here's a question that uses these ideas. If 60% of a department store's customers are female, and 75% of the female customers have a credit card at the store, then what is the probability that a customer selected at random is a female and has a store credit card? All right. Well, what things do we have? Well, if we come here, we're computing a probability. It has a female and has a store credit card. Now, this word "and," when we think of "and," that's an intersection. So this is trying to say, oh, what we're trying to compute is probability of female intersect credit card. That's what we're asked to find. So we want to make sure we understand what words mean. So that's what we're after. All right, well, that probably is not surprising given we just talked about, here's this formula for intersection. Okay. Now we have two probabilities. Well, one probability is given here, 60% are female. So the probability of being a female is 60%, or 0.6. Now we have one more thing, which we have to parse. And then there's this word "and." There's a 75% of the female customers have a credit card. Now, what is this? If we were going to write it in our notation, or what kind of idea is this? This is a conditional probability. It's saying, given that you are a female customer, then what's the probability that you have a credit card? So it doesn't say 75% of the customers have a credit card. It says 75% of the female customers have a credit card. So this statement says the probability that you have a credit card, given that you're a female. I do apologize for the wording on some of these problems. This one is from the book. Is 75%. So now what can we do? Well, we say, oh, well, this is great. If I want to know the intersection, what I can do is I can say, well, I can take the probability of just the one event times the probability of the conditional event. So how do we find our answer? If we think of these parts as being here, this is A, this is B, then this would be A, and this would be B given A. And then you're like, oh, lo and behold, if I want to find the intersection, you multiply. So this is 0.6 times 0.75. Which is something. I want to say 0.45? I don't know. We have technology, right? It's been a while. I think I can figure this out. 0.6 times 0.75. Yes, haha, 0.45. So the answer, what's the probability that a customer is female and has a store credit card? That's 45%. All right. Now, on to a really useful idea, which is that of probability trees. And I know there's a lot of words here. It's easier to sort of learn by doing an example, so we're going to go through and do an example. But the idea is we have a couple of events, and they're tied together in some way, oftentimes sequentially. Doesn't necessarily have to be sequentially. But there's somehow that they're connected. And we want to understand what's going on, so we're going to use a tree-like structure. to help us understand the different relationships. And I read this, and I just can see right away that I couldn't spell the word relationship last night. So I'll just cross that out, and hopefully nobody caught that. So what are trees? What's a tree? No. This is useful if you ever do any programming structures. They oftentimes use trees. The idea is you're branching. So you have an event in the book that likes to use the word start, and then you say, okay, do your first thing. You branch to all the possibilities. And then you say, okay, now that you've done that, keep moving down, and off of each one you keep branching off of all those possibilities until you reach the end. And instead of reading all this, let's actually go through an example. What's going to happen is we have a bag, and we're going to have some marbles. 2 red marbles, 4 yellow marbles. Go with the school colors. We got to be excited. We're bowl eligible. It's a great time. All right, school colors. So we're going to have our bag, and we're going to pull out a marble. We're going to know what color we pulled out, and then we're going to pull out a second marble. And there's an important thing here, which says, without replacement. So oftentimes they'll put this in one of 2 things, with replacement and without replacement. When we talk about without replacement, it's like after we pulled out the first marble and looked at it, it stays out. So it changes the mix of marbles in the back. If you put that marble back in, then you say, oh, I return to the original mix of things that are happening. So we'll have our start. I like to use the for the start, but the book says start. And I like my trees to grow down. The book likes to let the trees go to the right, but that's fine. Okay, so start, we have 2 rounds. So we say the first round. What are the possible things that can happen in the first round when you pull out a marble? What are the 2 things that could happen? Give you a hint, there's 2 things. Yeah, there's the only 2 things that can happen is that we draw a red or a yellow. So we go and we look at all the possible outcomes. So that's the branching structure. Each branch is a possible outcome, either red or yellow. Now, for each branch, there's also a probability attached to it, and that's the probability that we went down that branch. Okay, so what's the probability that we drew out a red marble? 2 over 6, because there's 2 red ones, and there's 6 total marbles. 2 over 6, I'll go ahead and write that as 1/3. All right, how about the probability that we drew out a yellow marble? It'll be 4 over 6, or 2/3. Now, a sanity check, if you add these 2 numbers together, what should they add to? They should always add to 1, because something had to happen. All right, so every time you're branching, the sum of the probabilities along the edges have to branch to 1. Okay, so next, we're going to do it for a second round. Okay, so what are the things that could happen? Well, we still are going to pull out marbles, so we still pick out either red or yellow. Now, I'm going to just keep track of what I pulled out from the first round. So I have red, red, or red, yellow. That's just to indicate I picked out red, then I picked red again, I picked out red, and then I picked out yellow. What's the probability that I picked out red in the second time? 1/5. Because the things inside the bag, we've changed our composition. Now there's only 5 marbles, and only one of them is red. So that's a 1 over 5. And the probability that we picked out yellow, similar idea, 4 over 5. So we branch on the other side. So we could have picked out yellow then red, or yellow and yellow again. And by the same idea, now there's 3 yellow marbles. So the probability that I picked out the red one will be 2/5. And the probability that I picked out a yellow one would be 3/5. All right. The last thing you want to do is once you have your decision tree, and most of our decision trees will be fairly short, you can make them long if you need it. The problems can be as complicated as they want, but we'll tend to just do 2 layers, maybe 3 on a crazy and wild day. But now that we're here, the last thing is to say, well, what's the probability that we ended up down in each part? Well, if I ended up red, I had to draw red, then draw red again. So it's this and that. So what's the probability that you end up down here is you follow the path from the start to the end. And you say, well, what's the numbers on each edge? You multiply. So 1/3 times 1/5 says 1/15. The probability that you got red is 1/15. Probability that you got red-yellow, 1/3, 4/5, right? You go follow your way down. So that would be 4/15. Yellow then red, 2/3, 2/5, 4/15 again. Yellow then yellow, 2/3 times 3/5, and you can write that as 6/15. Again, if you add all these numbers up, lo and behold, they do add up to 1. Okay, so that's the probability tree. So that's the example. But now, we said, look, use the tree, right? So we did the first part, draw the tree. That's what we did. Now we're going to use the tree. So what's the question? What's the probability that both marbles have the same color? How do we figure that out? Yeah, we just come to the bottom and say, which one of these pieces correspond to that outcome? So if I want to know the probability that they both have the same color, I say, well, come down here, and we say, add those 2 together. And so our answer, 1/15 plus 6/15 gives us 7/15. Slightly less than half. Not bad. Okay. So there's the answer. Now there's a second question that says, hey, what happens if we replace the marble after drawing? So it's with replacement. Well, what will happen? We'll have a very similar tree. The only thing that's different is going to be the numbers that we attach to some of these edges. So I can draw the same tree structure. The first layer doesn't care because nothing's happened. It's still, the first round is always the same, with or without replacement. If I come here, instead of 1/5 and 4/5, what are the probabilities that are going to happen? One-third and 2/3. You essentially reset, because with replacement, you're going back and saying, okay, let me try that again. So now it's the same situation that you faced at the start. And again, a 1/3 and a 2/3. So you follow your branches down. You say, well, what are the probabilities that ending up at the individual pieces? 1/9, 2/9, 2/9, and 4/9. So, what if you replace the marble after drawing? Well, we still look at those 2 situations. What happens there? Now what's our probability? If we add, we get 5/9. And 5/9 is bigger than a half. So without replacement, slightly less than a half that is the same color. With replacement, slightly more than a half. So, it matters, and you have to keep track of these things. So be careful with your problems. Make sure you understand what's going on. Any questions on this one? Okay. Well, do a really quick one. And I think this one was based on a problem from the book, maybe a problem from the homework, I can't remember. But we start at the beginning. We don't know what the experiment is. We don't know what M and N represent. We don't know what R and S represent. And in some sense, we don't have to. We can just say, look, all we know is this probability tree, and we're going to use it. So it's like we're becoming the tree whisperers. Let's listen to what the tree has to say. All right. So here's our probability tree. And one thing that they didn't mark is the probabilities of ending up at the individual locations at the end. So we can do that. So this first probability of ending up down here at the first R, multiplying 0.12. Then coming down here, 0.28, multiplying. Okay, then down. 8 looks terrible. 0.30. More precision. I feel like an engineer. And the last one, 0.30. All right. So, what is the probability of M given R? Okay, well, answer. How do we answer this? Well, we can say it's the probability of M intersect R over probability of R. Yes, that's our conditional probability. Now, how do we find the probability of M and R? Well, we look at our tree. We say, well, we need M and we need R. So we say the only way we can have that is if we went down this branch. First down to M and then down to R. So the probability of M intersect R, 0.12. What about the probability of R? Well, for the probability of R, we can say, let's just gather all the places where R shows up at the bottom. All the places that we could have reached that R was involved in. And what do we get? 0.12 plus 0.30. So that's 0.12 over 0.42. And I don't know that off the top of my head. And that's okay. That's why we came up with calculators. And this is approximately 0.2857, or about 28.5%. All right. So you can read off information. Like I can say, essentially the question is, look down here. Which pieces do you want to gather up? What's the probability of N intersect S? I made it sound like a very complicated question. It's actually a very silly question if you just think about it. What is the probability of N intersect S? You can read it off from the diagram. Sorry, what? Yeah, 0.3. N has to be true, and S has to be true. That means you have to be here, so it's 0.30. But there's this hint, and really the hint is not a hint at all, but it says what? Well, N has to be true, which means you're in this first branch. This is probability of N. And once you're in N, then you have to have that S has to be true. So this is probability of S given that you're in. So it's this data here is really coming down along the branch. So it matches with our intuition and our formulas that we've had before. All right. Well, that brings us to our next idea. Come on, paper, be nice. There we go. Independence. Ah, yes, college years, when everyone becomes independent. No, that's not what we mean. As a reminder, two events are independent if they're completely separate. Knowing the outcome of one does not affect the outcome of the other. It's like I have two different dice. They don't talk to each other. If I roll one dice, it doesn't whisper to the other dice, hey, I rolled a 5, you better not roll a 5. No, they're independent events. Okay, so what does that mean? Well, if I say, what's A given that B is true, it says, I don't care about B. I'm independent from B. It's just ask me, probability of A. Now, we talked about, well, how do you compute the conditional probability? It's probability of A intersect B over probability of B. And if you multiply across, lo and behold, you get the probability of the intersection, A intersect B, is probability of A times probability of B. And that's oftentimes how people will think about it in terms of computing probabilities. So the probability of the intersection is the product of the individual probabilities. That's independence. So I should point out, if this is true, this is true. Whoops, my board is extra slippery today. They're equivalent to each other. If one is true, and if only if the other is true. Okay, so let's look at an example. We have a table, and it says, consider the following table, and you look at it and say, like, I don't know what this means. But let's understand what it means. What we do have is we have essentially two sets of possible events. I'll think of them as sort of disjoint in some sense. And ABC is one set, DEF is the other. If it helps, you can imagine you're making plastic toys for kids, and there's two things you care about: the color, maybe red, yellow, blue, the shape, square, circle, triangle. And now you say, okay, so I have, again, one of three colors, one of three shapes, and what we have here on the inside is we've essentially said, what's the probability of having that combination? So if this is a red square, it's a 20% probability. So 20% of them are red and square, and so forth and so on. All right, so that's the table. And what's true? Well, if I sum up the rows, then that's the probability. So again, if we think of things, I'll go ahead and write this down, just in case it helps. This is red, yellow, blue. This we can think of as square, circle, triangle. If I add up the row, well, that really says, okay, really I'm adding up the probability that you're a square. So this total here, that's just a probability of just D. And then similar probability of being a circle, probability of being a triangle. If I add up the columns, well, that becomes probability of a certain color. We really like red. Not so much yellow for some reason. And then blue. Now the question, which pairs are independent? So when I talk about a pair, I mean I have one of ABC and I have one of DEF. How could we figure that out? How can we figure out which pairs are independent? Are there any pairs that are independent? It's just something that's not meant for us to know. What can we do? Well, essentially, if I look at a square, if I look at this square right here, one way for us to think about what this square represents is that's the probability of A intersect D. It's the probability that both things are true. So that's what every individual cell represents. If this were independent, what would this quantity need to be equal to? It would have to be equal to the probability of just A times the probability of D. Well, the probability of A is 0.7. The probability of D is 0.3. If you multiply 0.7 times 0.3, what do you get? 0.21, which is not 0.20. So A and D are not independent. Are there any that are? Well, let's just quickly check. I come to 0.03 and I say, is that 0.1 times 0.3? Yes, no. Yes. So there's an independent one. Does 0.3 times 0.2 equal 0.07? No. How about 0.4 times 0.7? Is that 0.28? Yes. How about 0.4 times 0.1? Is that 0.05? No. 0.2 times 0.4, is that 0.07? No. 0.3 times 0.7, is that 0.22? No. 0.1 times 0.3, is that 0.03? No. 0.2 times 0.3, is that 0.06? Yes. So there are some independent pairs. And they are, we have the pairs, I'll put them in B, D are independent of each other, A, E are independent of each other, and C, F. All right. Well, let's do these last two, and then we'll call it a day after that. Find the probability of D given B. Well, we know this is conditional probability. So this is the same as the probability of the intersection divided by the probability of being in B. If I want to find D intersect B, I come to the table and I read it off. D intersect B, that is our 0.03. If I want to find the probability of B, I come down, sum up, that's 0.10. And if you clean this up, this turns out to be 3/10 are just 0.3, so 30%. What about the probability of B given D? Will that be the same? If you switch, does the order matter? Well, there are going to be some cases where they match, but we should be suspicious. Whoops, B intersect D over probability of D. We've already talked about the top. That's still 0.03. It's the same thing. What's the probability of D? It's 0.30. So if you take 0.3, divide by 0.30, what do you get? You get 0.1. So be careful. Be careful. Order matters. D conditioned on B is not the same as B conditioned on D. But next time we'll start with Bayes' formula that says they are connected.